Okay. Okay. So here we were in the last class. So finally, after discussing all the things involved in OFDM as a multi-carrier modulation scheme, we had come to the final OFDM block. And what all things does it contain, by the way? So here it is, the block. I will not go into much detail. It's been discussed already. So you take in the data, do modulation, BPSK, QPSK, COM, whatever it is. COM it is actually. Okay, do the modulation, convert the data from serial to parallel. You can see converting the data from serial to parallel modulation. All those things are missing here. Okay, this X here indicates the data which has been converted from serial to parallel. Okay, so do not get confused. All those data things are missing here. So here on from IDFT onwards on this block shows. So you take IDFT, convert the data once again from parallel to serial. And since you are talking about a channel which is in time domain, that is the reason why IDFT was taken to indicate the frequency to time conversion. Okay, so we discussed in great detail what's the deal with adding this cyclic prefix. As I told you, it was to make sure that the linear convolution that happens in the channel is faked by a circular convolution. And also we discussed the frequency domain equalization, that is a possibility here, since you have employed the converted the data in the frequency domain here. So you get that particular FEQ. Yeah, let's get that. Okay. So let me clear all the drawings. Let me continue now. Okay, so let's go into the terminology. Okay, so what are things, by the way? Actually, a close-up of OFDM passband transmitter. You have your symbols here. What are the symbols, by the way? So if at all you have combined 2 bits at a time, then the symbol, actual symbol is 4, or 4 PSK. If at all you have combined 4 bits at a time, then your symbol is 16 Okay, so that's what your symbol is. And see here, whatever the speed, now since you have employed, if at all you are going for a 64 point IF50, that means your bit rate has been reduced 64 times. So now all, if at all you are going for 4 point IF50, then number of subcarriers is called 4. If at all you are say taking 64 point IF50, the number of subcarriers is 64. Okay, now are you getting the coefficients of your FFT or IFFT? They are nothing but subcarriers. Okay, they are nothing but subcarriers. That is the standard word used in OFDM. Okay, so your actual samples are X, but then you are taking cyclic prefix also, right? So we are discussing these last few of these symbols will be actually appended here in the beginning. Okay, to make a data word which is bit longer. Okay, so this is the overhead, and we discussed in great detail. So how to decide the cyclic prefix, and you're telling it is based on G, right? Related to the guard interval, how many number of additional bits we need to take. 2 things, to take care about the guard band, and then to get the CP, right? What should be the actual length of CP, because larger length of CP, it introduces the rate loss that we discussed in the previous class. So that's it, you get your actual data, then afterwards append the CP, then convert the data from parallel to serial. As you can see, B into 1 plus G, see, this is the overhead involved. Okay, this can't be 0 anyway, this can't be 0, this can't be 0, but this G here takes into consideration the guard bits as well as CP together. Okay, so guard bits only, they will serve as cyclic prefix. Then you have to put it on an analog channel only, so digital to analog conversion, it will happen anyway. You use a continuous carrier. Okay, then you go for some sort of multi-carrier, some sort of modulation. Okay, using a single carrier. See here, you will use a single carrier only, but then since you have taken FFT here, it gives you an impression of multi-carrier. Okay, so that is the case. So finally you get a multi-carrier signal, even though you are effectively using a single carrier here. Okay, even though you are using a single carrier. Okay, what next? Yes. So here is a description of what all things. So nominal bandwidth. So here is an example of Ofdm parameters for say 10 megahertz value. Okay. So out of say, if at all are using a bandwidth of 10 megahertz, then out of that the nominal bandwidth, okay, for symbol B is 7.68. Why? Because the total bandwidth at our disposal is 10 megahertz. As I told you, the guard band and all those things are coming into picture, right? That's why what we actually get is 7.68 megahertz only. And L, the number of subcarriers, C, size of F50 and IF50. So you might, we are in classroom, we are doing 4.50, 8.50, right? See, they are employing the commercial values, you can see are something like 512, or you can see 1024, even it can even go to 2048 also. Okay, that is the L value that they take usually. Okay, so out of that means now whatever the bandwidth you have, it has been broken down into 1024 parallel streams. Okay, broken down into 1024 parallel streams, but there is a catch involved here. Out of this total L, around 0.07% will go for the cyclic prefix, rightly so, that will go for cyclic prefix. And how many carry the actual data? See, you can see out of all these subcarriers, only 600 of them carry the actual data. Remaining all will carry either the null subcarriers or the pilots. Okay, null subcarriers are there probably for some sort of signaling or for indication. Pilots, as I told you, right, in the block diagram of OFDM, we were discussing that if at all you happen to know H, and if at all I happen to know Y, then what we can do, X can be derived from, how do we derive X? X equal to X into H into H into X is equal to Y, right? This stories were told to you. Input and channel will multiply in the frequency domain. So once you have the output, the input can be recovered by dividing this Y by H, right? So all these things were told, but who knows this H, by the way? So the way to know the channel frequency response, or so-called channel state information, or whatever they call it. Okay, channel status, say channel impulse response. Okay, so the trick is for every 100 symbols or every 1000 symbols, what you do, or every large symbol that you carry, you put a known sequence called a pilot in between. So from this pilot, you know what you have sent, and then there is a channel which is constant for at least certain period. The channel doesn't behave much frequently, right? The channel behavior will change maybe once in a minute, once in a second, or once in a 0.1 seconds. Okay, so then what you will do is, but your speed is much higher, right? Your bandwidth is 10 megahertz, or actual bandwidth is 7.68 megahertz. That means 1 by that is your timing instance, okay, at which you are sending the data. So what you do is, out of the entire data whatever is sending, you in between send the known sequences which will allow you to estimate the channel behavior. Okay, pilots are those known sequences which are added in the symbols usually, so that at the receiver, before you start receiving the actual data, you can estimate the channel behavior by this known symbol. Okay, so that is a pilot reception. Okay, that is what a pilot reception is. Okay, so then data subcarriers. Okay, so out of 1024 IF50 coefficients, only 600 of them carry the actual data. Remaining we will go for overheads, pilots, then guard bits, and so and so. The subcarrier spacing is 15 kilohertz. That means 2 subcarriers. As I told you, orthogonal subcarriers, whatever we told you, right? Whatever there's the spacing between the 2 subcarriers. It's a standard. Okay, 15 kilohertz is the minimum spacing between 2 subcarriers. Whatever the size of FFT use, whether you use a 256.FFT or 2048.FFT, the subcarrier spacing happens to be 15 kilohertz usually, and the sample time, by the way. Okay, so 1 by this particular thing into, okay, guard symbols for this particular case of 10 megahertz and FFT size of 1024 is 72 symbols. Okay, it is a case they are taking. There are several values. Okay, 10 megahertz is one standard bandwidth, and OFDM symbol time here is 142.7 microseconds. Okay, 142 is a OFDM symbol time. Okay, per symbol. Okay, so whatever symbols you have sent is spanning this much amount of time. You can see this is a very small number, so sending some pilots and all, it's not going to hurt that much. Okay. Okay, now let us continue and understand what can possibly go wrong. Okay, so here's a very interesting numerical that we all can go through. Okay. So what does it talk about? Go through this, if at all is taken into consideration the kind of modulation and used and its impact on the rate and all those things. Okay. So it's a recorded video. I will be recording this also, so you can go through this at your leisure. Let me just continue. Okay. So now let us talk about what can go wrong. Okay, let us talk about where things can go wrong. Okay, so there are two things that should be taken into consideration. As we told you, what do you do is you have this data, then you took the DFT, right? You took the DFT, IDFT, and what happened was the data converted into orthogonal overlapping subcarriers, Then afterwards, you send this thing to a channel. Now, what will happen in the channel? So two things will happen in the channel. One is there is time delay spread in the channel, right? Due to multipath, there is time delay spread in the channel. Okay. Second thing that can happen in the channel is the relative movement between the transmitter and the receiver. The relative movement between the transmitter and receiver that can cause the carrier frequency to shift here and there, right? The carrier frequency, that's something called as Doppler shift. Do you know what is a Doppler effect? Doppler effect is when two things, right, have relatively moved towards each other or away from each other. The frequency F is going to be either plus or minus FD, right? Say 100 may become 101 or it may become 99. Not a big number, right? 100 becoming 101 and 99. But then your carrier frequency, by the way, has an elevated effect, because if it all take 1024, then everything has boiled down to 100 divided by 1024. So the small change is going to make the difference. Okay. So let us read this author's version. The timing offset of the symbols and the optimal timing instance need to be determined. Okay. So when shall we receive the data? Then the second is the receiver must align its carrier frequency as closely as possible to transmitted carrier frequency. Remember, there was this thing called as experiment called as phase lock loop, right? The PLL. Remember that there was this experiment called as PLL or phase lock loop. So it is all about you receive the data, and then afterwards, for all the things, whatever that is taught to you, amplitude modulation, frequency modulation, phase modulation, for all those things to work at the receiver, one requirement is your carrier at the receiver should be in phase with the carrier phase, whatever you have, right? You have an audio frequency oscillator at the receiver, which is having the same carrier frequency that at the transmitter also. Both of them should be in phase, right? That's what PLL does, phase lock loop. It's going to match them in phase. That is when the demodulation occurs. If they are not in phase, then we do not have the so-called frequency synchronization, and there will be problem. Okay, let us analyze these two issues individually now. Okay, so here we are talking about a timing synchronization. What can go wrong, by the way? So for timing synchronization, you can see this is the carrier frequency what we have here. This is the carrier frequency what we have here. And because of the movement, relative movement, there will be some Doppler effect, and the carrier frequency may change. Okay, carrier frequency may shift a little bit here and there, which is a function of time over a time, right? The things are moving, right? Right. So over a period, if at all you check it, the frequency looks same, but then within a certain time instant only, the carrier frequency is shifting, right? Say you are driving on a vehicle, there is a mobile tower, and you are driving a car, and you are driving at a in a location such that at some instance you are moving towards, right? Some instance, say you are here, okay, there is this tower here, and you are moving from a road in a car here to here, right? At some instant you are going away from the tower, and then after at some point you are moving towards the tower. So what's going to happen? Okay, what's going to happen is the Doppler frequency, the carrier frequency is going to change. The carrier frequency is also going to change, creating the synchronization issues, creating the synchronization issues. This is a problem. Okay, this is a issue. So what to do, by the way, what to do? If at all the small things only, small shifts in the timing instance are going to create that much problem. If at all you want to be immune to this, what you can do is increase the width of the symbol, which you have done. You have increased the width of the symbol, fine, right? Say if at all you're taking 1024 point DFT, that means you have increased your symbol width much larger, so that this tiny changes in the time instance do not affect you that much. Okay, the second thing is you have taken sufficient delay spread taken care. Then afterward there is a guard band, there is a guard band also which you have designed properly. Okay, then what is possibly going to happen? Okay, so you can see here they are talking about, if at all your PLL is not performing well, the phase lock loop, analog or digital one, whichever you are using, it will, but it takes time. Okay, so here let us see what author has to say. In case that perfect synchronization is not maintained, still possible to tolerate timing offset without any degradation, as long as the timing is in this particular range. What is this TG, by the way? TG is the guard time, and TM is the maximum channel delay spread. That means this is the rule. Usually whenever you are deciding, while deciding the a number of subcarriers to be used, you usually take your bit duration to be 10 times the time delay spread to take care about this. Okay, 10 times the time delay spread to take care about this. Okay, so that is why this is the way to encounter this particular thing, the guard bits and the and the large value of the subcarriers that you have taken. Okay, so these things can be tolerated. Okay, so timing synchronization is not a issue. Okay, so are there going to be any losses, by the way, because of this? Yes, there is a SNR loss, a relative loss. That is why the change is indicated by delta. Okay, so decreases. SNR should be good or bad, by the way. SNR always should be a higher value, but then you can see it decreases quadratically because there is a square term here with the timing offset. So what do they say? Longer OFDM symbols are increasingly immune to timing offset. Okay, that is, more the number of subcarriers, larger the pulse width, it is always good. But larger pulse width actually means what do they say? Let us see it in the frequency synchronization. It's like a bootstrap thing. You try to make this thing better in the performance in the time domain. In frequency domain, it is going to suffer. Anyway, okay. So what do they say? SNR decreases quadratically with the timing offset. Okay, fine. Okay, so since in general you have taken care things here, timing synchronization errors are not that critical as long as induced phase changes corrected. Fine. Okay, but there is a catch here. So till now, how do we tackle the timing synchronization, which occurred, by the way, due to multipath issue also? Okay, we took care of the solution by making the data speed as small as possible, which is done, by the way, by increasing the FFT points. But then let us see the next issue at hand. Wait a second, got some glitch here. Okay. So yes, that brings us to the second interesting issue, the frequency synchronization. So what is this frequency synchronization? frequency synchronization is your ability for this whole fairy tale thing called IFFT to work. You told that you are not going to use several local oscillators. You take IFFT at the transmitter, FFT at the receiver, right? Fine, everything works. But then in the channel you suffer Doppler effect, and because of that, your carrier has now the center single carrier now shifted. So that's what happens. Once the carrier shifts, right, all these subcarriers also sort of slightly dwindle. And when that happen, see here, the magical way it works is because whenever you are trying to sample this particular peak here, all other contributions from all the neighboring ones is actually zero. Okay, but then if at all one of these carriers slightly moves towards the left or right, one of the carriers moves towards the left or right, can you imagine what's going to happen? What's going to happen? Then when you go and try and sample, you can see this particular instant is shown here, where receiver thinks that this is the carrier frequency, where receiver thinks that this is the carrier frequency, whereas your actual carrier frequency is this particular point. So when that happens, usually you may end up getting a demodulation errors. You may end up getting demodulation errors. This is one thing that limits you by using the number of subcarriers. So that is why, as I told you, if at all you want to go for large number of subcarriers, say of 256 is fine, 1024 is fine. You want to go for 2048 to tackle more amount of fading, then what's going to happen? Eventually your subcarriers are going to come so close that a slight change in the frequency in synchronization is going to affect the complete data reception. So as you can see here, the statement, okay, SNR decreases quadratically with frequency offset. Yeah, it was there earlier in timing offset also. Decreases quadratically with the number of subcarriers. So you can see here, there is a limit on the number of subcarriers that you can use. Large number of subcarriers allows you to tackle the time delay spread well, the fading well, but then it is going to affect in case there is a frequency synchronization issue. So one should be very careful. Okay, so these are the things. Timing synchronization problem tackled well. Frequency synchronization problem, okay, is the bottleneck which limits the use of the number of FFT points. The next interesting thing that we will be discussing, which we will do in next class. Okay, HOD is scheduling his class, I guess. Okay, I will stop this thing in the 2-3 minutes. It's called as peak to average power ratio. Let us do a small exercise now. Okay, so I will take this number. Say, Sushma, are you there? You are there, right? Okay. Say I have 2, 2, 2, 2. Okay, I have this sequence 2, 2, 2, 2. Okay, so can you tell me what is the peak power for this particular thing? Can you see? Can you tell me if this is my sequence, which is the value which is having highest power here? Expression for power, by the way, square. Okay, so you can see 2 square. So power of this is 4, 4, 4, 4. Okay, 4, 4, 4, 4. I will not take the average. Okay, 4 values, right? Divide by 4. Okay. Now, if at all I take, so what is the PAPR of this particular peak to average power ratio for this particular case is 1. Okay, because what is the peak power? Yeah, are you? Okay, so I think HOD, okay, we'll stop here. Okay, we'll stop here. Next class, we'll discuss this all important peak to average power ratio. See, PAPR is the reason why you are using 2 technologies. You can let me remind you once again, if at all there is a tower and then there is a mobile phone, to send you data from tower to the mobile phone, we use something called as OFDMA. Okay, from tower to mobile phone, what we use is called as OFDMA. Whereas the communication from mobile phone to tower, uplink, what we call, is done by using a different technology called as SCFDMA. See, they sound similar, but they are completely different. Okay. So the communication from tower to the mobile is called as downlink, whereas the communication from mobile phone to the tower is called as uplink. The technology for uplink is OFDMA. Technology for downlink is SCFDMA. Why two different technologies? It's very interesting thing. And the reason why different technologies are used is this term here, the evil, called peak to average power ratio, PAR or PAPR, as it's usually referred to in the literature. So tomorrow we'll start this all interesting thing with PAPR and how we are forced to use a variant of OFDMA called SCFDMA to tackle this particular issue. Okay, so this issue is still there even in 5G, and 5G also employs something similar approach. Okay, not a homogeneous technology for uplink and downlink. Okay, thanks for joining the class. Now let me stop this thing here. Bye.